I would say that there is a change of there is a change in like there's a change in the entropy is always going to be the same. Like if like when you have like hot water, I guess if you have hotter water, sugar dissolves a lot easier than if you just have colder water. So there is definitely going to be that kind of relationship with that. But yeah, there is entropy and then there's enthalpy involved with that process. I can give you the full details about that off the top of my head.
Yeah, it's a hard one. So lab 5, our big technique, I think, was filtration. And so let's see. For filtration, just go over if you don't remember all the nuances of that, just look on lab 5. They have a little PDF. It's about 2 pages on filtration. Just tells you, you got to fold up your filter paper, put it in a Buchner funnel, weigh it beforehand if you've got a solid, and then to remind yourself that you weighed it, you can tear off the corner, but you need to tear off the corner before you weigh it. Anyways, so let's see. So there's a piece of vocabulary that I wanted to go over because I thought it might trip you guys up, which is if we have a filtration. Do I have a good marker in my pocket?
I think you might.
Okay, so if I'm going to have, again, expertly rendered in 3 dimensions this time. I know. So, okay, this is my solid, you can tell because I just told you. And here, okay, so this is my solid that I want. This is my beaker right here. And I'm going to pour that over a Buchner funnel. It's like you're there, right? It's like it's really happening. Okay, so what I'm going to do is that I'm going to try and separate out my solid. So this is desired solid. Right now, this liquid that I'm pouring off, this is the supernatant. This is what the supernatant is. This is called supernatant. You're going to hear this in biology too. It's the liquid that's basically in your container with your solid, with your pellet. This is a supernatant. When I pour it over the filtration, when I do the filtration, so now I'm going to pour liquid through. Little movement here, flow. That's some liquid. Okay, so the liquid that's pooling in the bottom here of my flask, this is going to be my filtrate. And my solid would remain here in the Buchner funnel. So it's the supernatant versus filtrate is kind of a piece of vocabulary I thought you guys might be having a little trouble with because it might seem like this kind of the same thing, and it might be hard to figure out what's what.
In general, they're both the same thing. It's the same switch except that like the supernatant acids like fell through the funnel and the filtrate.
Yeah.
Yeah, but sometimes like it would maybe still include your desired solid since it's like if you have like a I don't know, if your filter paper isn't like doesn't have holes that are small enough to catch some of your things, you would have your filtrate would still contain some of your stuff.
And by the same token, if you think about here, there might be little particles of your stuff kind of floating around in it still, and when you pour it off, everything, most of those little particles that would be in your beaker here are going to hopefully, in the ideal case, get stuck on the filter paper, and this should just be a pure liquid without the particles of your desired solid. That's what you're going
But
for.
essentially, they are the same thing after a very specific process, after doing the filtration.
Yeah, it's just like a lot of times they ask you questions about the filtrate, the supernatant, this kind of thing, so I want to make sure that you don't get those terms confused so you can answer them correctly. The conductivity units are microsiemens per centimeter. Yeah, I think that's the main thing.
The main thing that you want to take away from that, one of the main things you want to take away from the slab in particular is charge, like if you have something that's dissolved in the liquid that's charged, i.e. if you have like a salt like sodium chloride dissolved in solution, that is going to carry a charge a lot better than something that does not dissociate as well, such as a weak acid or alcohols, which don't really dissociate very well in water. So any questions about that?
Lab 6 is a titration.
And that's the weak acid maybe.
Yeah. I think the main, again, vocab for lab 6 was the, if I have a burette and I've got the burette in the flask. This is my burette and this is my flask here. There's lots of gradations on this. This is a very well gradated burette. So this, the solution in the burette is your titrant. And the solution in the flask is your, I drew a beaker, but it's your analyte. So that's the main piece of data or vocabulary that you need to know.
Then there's also a couple of other ones too. The endpoint and the equivalence point.
Oh goodness, yes.
So the endpoint would be like that refers like the endpoint refers specifically to the color change of your.
Well, I'll do it over here.
Okay, cool. So I guess I'm just gonna write it out. I guess.
Okay.
Well, I'll draw this movie plot first. So where you have. Well, I think I'll also draw the buffer region as well. So we're gonna have something like that. So the equivalence point is right here. It's the middle of that sigmoidal shape, in the middle of that S there. The equivalence point is basically when you have equal concentrations of like basically the weak acid and this like I'm just double
A
checking.
minus HA.
Yeah. A minus the HA. That's right.
Yeah, equal each other. The concentration of A minus, if you're doing equals the concentration of HA.
That's the equivalence point there. And there's a buffer region as well that is also important on your titration plots, where this is just where your weak acid or weak base, whatever you're going to be working with, that's the optimal point where these you're seeing some resistance in the change of resistance to the change of the pH during that mode. And remember as well that the equivalence point is a very, very important point because at half of the volume or half the concentration that you added, you will see you'll have your pH equals pKa. And that usually would also be somewhere in the middle of your buffer region. But that's neither here nor there. So let's see here. I'll just call this 10. Call this 5. So again, the equivalence point is the middle of that S. Half of that, like if you're looking at your plots, like basically if you add half the stuff, that's where your pH is equal to pKa, or should be equal to pKa. And when you're doing your percent error, make sure you're doing that with the logarithmic function as well. Make sure you're not just using the pKa value. So for example, for the acetic acid, you would have 4.7. And for example, you want to actually use the log function of that, I believe. Is that right? Or what was it? It was the exponential. Oh, Christ.
The under the decimal?
Yeah. The Henderson, according to Henderson Hasselbalch, right?
pH equals negative.
pH is equal to negative.
pKa plus ln. Yeah.
There we go. You guys know it better than we do.
Yeah. pH equals pKa plus ln of concentration A minus over HA.
Okay, so it's the natural log. That's what's right.
So on this slide, grafting, where's the end point?
The endpoint. Okay, the endpoint is while you're watching your flask. The endpoint would be where if you're using phenolphthalein, for example, that's where it turns from clear to pink.
Is that when it drops in there, the first red color, and when it just
No,
drops, or when it stays?
when it stays that color. I mean, when you add it, there will it's not fully mixed yet until you'll see areas of higher concentration base just kind of floating around, but it's not quite equilibrated yet. But once it turns that characteristic super pink color, that's when your endpoint is.
And then you keep measuring it to get to equivalence, so it doesn't have the same point.
They're not necessarily the same points. The pH lab that we did, we were just trying to see if the particular indicators were good for these particular things. Where the equivalence point was not within for some of the examples that we did. The equivalence point was not exactly equal to or at least not even close to the region